All right, so yes, happy Halloween and happy Friday. It's the end of 4th week, which yeah, I guess we're just chugging along here. Okay, so today we'll talk about multivariate sampling, and this is all about kind of generating samples from kind of more than one variable at a time, right? And so everything we've covered so far has been generating samples for univariate distributions. So we have like some f of x, and then and you generate random values from it, right? And so we've got a bunch of tools in R. You've got you know, a bunch of R norm and R binom and R beta and whatever, all sorts of things. And then we looked at tools for dealing with distributions that aren't as easily found. So, you know, inverse CDF and rejection sampling and all of that. And but now we want to consider, well, what do we do if we have to generate kind of a joint distribution, x and y together, okay? Or x1 and x2 and x3 and x4. You know, you might have multiple x values and you want to generate values together. And if you just generate them separately, then all of these things will end up being independent. And in some cases, you don't want them to be independent. You want there to be some kind of joint distribution. So today we're going to look at bivariate distributions. And then next week, well, and eventually we're going to get to higher dimensional distributions, okay? But right now it's just going to be bivariate, okay? And then next week, I'm going to introduce the topic of Markov chains, which is going to be important. And because there's a lot of, I guess, Markov chain Monte Carlo, MCMC. And so so we'll look at Markov chains next week, and we'll build up and work our way towards the Metropolis algorithm and Gibbs sampling, and those are ways for us to generate samples from higher dimensional distributions. But today, just bivariate distributions, kind of using tools that are available to us right now. All right, so we're going to just start by looking at a bivariate discrete distribution. And so we're going to say, you know, let's say we've got some random variables x and y, okay, random variables x and y, and they've got this joint probability mass function. So it's a discrete distribution. So we've got a PMF, and you know, if you sum up all of the probabilities, they add up to 1. And so, you know, x takes on the values 0 and 1, y takes on the values 0 and 1. And we can see that that x and y are not independent, okay? Because when x equals 1, y has an equal chance of being 0 or 1. Y, you know, probability of y also being 0 is 0.1, and y being 1, I'm sorry, y being 1 is 0.1, and y being 0 is 0.1. So when x equals 1, y has an equal chance of being 0 or 1. Whereas when x equals 0, it's much more likely or biased to be 1, right? Because the probability of when x is 0, the probability of y being 1 is 0.6, whereas the probability of y being 0 is only 0.2. So we can see that they are not independent because you know, these are not kind of proportional across the rows. And so how can we generate samples from this distribution? Well, we would approach this in a fashion that is similar to a discrete PMF using inverse CDF, okay? What we're trying to do is we're trying to map kind of the coordinates x and y, the pairs of coordinates x and y, onto the interval 0 and 1, okay? Which we can do because the PMF, the total PMF, will add up to 1. So if we take a look at that top corner, 0.2, that's going to be our first value. Probability 0, 0 is 0.2. And then as we go, the cumulative probabilities, if I go down the column, 0.02 and 0.1, if I add those together, that would end up being 0.3. So if I take probability 0, 0 and the probability of 1, 0, those add up to 0.3. And then I go over to the next column, and if I add up this, this, and this, they add up to 0.9. And if I add up all four, we're going to get 1.0. And so we can do, we can generate values by taking values from the random uniform distribution. And if u ends up being less than 0.2, we're going to set x equal to 0 and y equal to 0. If u ends up being between 0.2 and 0.3, ends up being between f1 and f2, we're going to set x equal to 1 and y equal to 0. And if u ends up being between 0.3 and 0.9, we'll set x equal to 0 and y equal to 1. And if u ends up being between 0.9 and 1.0, then we will set x and y both to 1. Okay, and that's that. Okay, and you could achieve this with a bunch of if statements or something. And I wrote up some code so we have a vectorized version. We don't have to use any if statements. But I'll show you. You can take this same concept and apply it to a more complex distribution. I mean, I don't know how much more complex this is, but now x can take on the values 1, 2, 3, 4. Y can take on the values 1, 2, 3, 4. And we have, and this is kind of the joint PMF, probability mass function. And if I add all of these up, they would add up to 1. And we would now we have kind of 16 values for us to calculate here. Okay, so we got 0.02. That's going to be the first value. And then the next value, f2, is going to be the sum of 0.02 plus 0.03. I'm just kind of going down the column. So 0.02 and 0.03 add up to 0.05. And then if I take the first three values, 02, 03, and 04 add up to 09, 0.09. And that's P11, P21, and P31. And so on and so forth, okay? And we're going to kind of apply the same rules where if I generate a random value from u, and if it ends up, if my first value is less than 0.02, so it's between 0 and 0.02, like 0.015 or something, then we're going to set x and y equal to 1. Okay, x and y will be 1 and 1. That's what we'll do. If I generate a random u and it ends up being between 0.02 and 0.05, okay, then we're going to have x is 2 and y is 1. Okay, so that would be like if my random u ends up being something like 0.03. All right. And then, you know, so on and so forth. If the random u ends up being between 0.05 and 0.09, then it's going to be correspond to x is 3 and y is 1. Okay, and we fill that out until we get to the end. And sorry, I messed up my LaTeX here, but you know, and so if our last value ends up being between 0.9 and 0.10, then that will correspond to the values x is 4 and y is 4.
Mama, why do you have glasses?
Okay. All right. So is that all right? And we can write the code. We can write the code for this by using a whole bunch of if functions, okay, or if statements. So it's possible to achieve the result with a bunch of if statements. But in R, and you know, especially when it comes to kind of Monte Carlo stuff, if you are able to avoid if statements in something like this, that will speed things up, because an if statement in a function will make the function not vectorized, right? Because if statements can only take one value at a time, so you can't vectorize if statements. So I'm providing a solution for being able to kind of get the results that we want without having to write a whole bunch of if statements, okay? And that will also allow us to keep things vectorized. So it just requires a little bit of creativity here. All right, so first I'm going to enter the probability matrix, okay? So I'm just entering this, you know, these values, 0.02, 0.03, 0.04, 0.01, 0.06, 0.04, 0.2, 0.1, so on and so forth. they're being entered into the probability matrix here. Okay, so so here I do this. I've got just a vector of 16 values, and I'm going to say we're going to enter this by rows. Number of rows is 4. Okay, now R stores matrices as vectors, and so I can get all of these values here: 0.02, 0.05, 0.09. The next one will be 0.1, so on and so forth until I get 0.9 and 1.0. I can just take these things, take the matrix, treat it as a vector, and ask for the cumulative sum. And we see that we're going to get the same values, right? If I go 0.02 and add 0.03, I get 0.05, and then the next value 0.09, and so on, 0.1, 0.16. And so we can get all the cumulative probabilities. I get a vector of cumulative probabilities here. Okay, is that all right? So, so here I've got my probability matrix. I've got my cumulative probabilities. And then what I'm going to do is I'm going to create a vector of kind of corresponding x values and corresponding y values. So if I think of the cumulative probabilities and the values that x and y take on, x is going to go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Whereas the y values will go 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, and so on. So I'm going to create my x values by repeating the vector 1 through 4 times. Okay, so x becomes 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And then I'm going to create my y values by repeating the values 1 through 4. But I'm going to say each equals 4, and that will give me 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, and 4, 4, 4, 4. Okay, and so we can see that this 0.02 kind of corresponds to, yeah, if I get 0.02, that's going to give me 1, 1. And then this 0.05 is going to correspond to x is 2 and y is 1. And 0.09 is going to correspond to x is 3 and y is 1. Okay, and that's what I've got here. 0.02, 1, 1, 0.05 is x is 2, y is 1, 0.09, x is 3, and y is 1. All right, and so this is kind of my solution, for going from u to x and y values. All right. So what I'm going to do is I'm going to compare the u. So anytime you write code and you're trying to figure out, does it work? What we're going to do is we're going to, what I always recommend is that you start off with a very simple case. Just start off with like one case, run it through and see if it's going to give you what you want. So here I'm going to just say u is 0.01. And I know if u is 0.01, then it should return x is 1 and y is 1. And so, and then we'll try out maybe a value like 0.03. And if u is 0.03, then it should return the next value where x is 2 and y is 1. Okay, so we're going to kind of try those out. So what I'm doing is I'm going to say, all right, u less than cumulative probability. That is going to look at this vector here, and it's going to return a vector of true falses. Okay, and it's going to be true wherever u is less than cumulative probability. Okay, and then which will turn the true falses into numbers, right? So it'll say which values, where is it true? And it's going to say it's true for 1, it's true for 2, it's true for 3, it's true for 4, it's true for 5. And what we want is we want kind of the leftmost value where it's true. So I'm going to say min. Okay, so we're going to kind of the first value that ends up being greater, the first cumulative probability that ends up being greater than u. Okay, so if u is 0.01, the first value that ends up being greater than 0.01 is the very first value. So that's going to be position 1, which corresponds to x is 1 and y is 1. Okay, and so here's my next case. U is 0.03. So 0.03 is in between 0.02 and 0.05. And so we want this to kind of correspond to x is 2 and y is 1. And so we're going to say u is 0.03. So we're going to, again, do which values are less than cumulative probability. It's false for position 1, but it's true for position 2, true for position 3, 4, 5, and so on. And so which values, it's going to say this vector is going to be 2, 3, 4, and up through 16. And the smallest value, the minimum of those, is going to be 2. Okay, so I say, all right, x value is position, and that's going to correspond to 2. And then the y value is position, the second value, and the y values vector is going to be 1. So that's going to correspond to x is 2 and y is 1. All right, and then so let's just kind of try out another one. If I say u is 0.89, okay, it's only going to be true if I compare u to cumulative probability. It's only true for 15 and 16. Okay, so if I say, well, which u's are less than, which has this statement true, cumulative probability is greater than u, it's going to be true for 15 and 16. And the minimum, the smallest one, is 15. Okay, so that gives me position 15. And position 15 corresponds to x is 3 and y is 4. All right. And that's what we want, okay? And so here I've achieved being able to get the x and the y values that I want without having to use a bunch of if statements, right? I just kind of line everything up and I just say, all right, what's the u I get and where does it kind of fall and what values of x and y does that correspond to? So I think it's a pretty good solution for avoiding having to create a whole bunch of cases here, right? Okay, so then if I wanted to generate a whole bunch of these values, again, we want to avoid, it's generally recommended to kind of avoid loops and if statements and things like that. If you use a loop and an if statement, don't feel bad. It's totally fine. Okay, it just might take a while to run. Okay, but who cares? There's always kind of a joke, right? Like, why have a loop run for 6 minutes when you can spend 6 hours optimizing it? So it runs in 6 seconds. But anyway, it's fine. If your code takes 6 minutes to run, your code takes 6 minutes to run. It's not a big deal. But if you can think of a way to kind of optimize it so it runs in 6 seconds, then great. But it might take you a while to figure it out. So anyway, so here I'm going to just generate a whole bunch of u values. Okay, and if I just tried to apply this naively, which is what I did at first, I was like, okay, well, I'm going to just plug in the u. What R is going to do is it's going to take all 10,000 u values, compare them. It's going to recycle these two vectors. And it's just going to return one minimum value. Okay, so I realized, oh, you know what? I need to apply this function for every single u value. Okay, so I wrote a position function, which is going to give me back that number that I was looking for, the position where u is less than the cumulative probability for the first time. So I write the position function, and then I use the apply function in R. And so we apply to this, I take all of my random uniform values and I turn it into a matrix and I use the apply function. So I'm going to say apply on u in dimension 1. We're going to apply the position function. And so this is a vectorized operation to do all of this. And we're going to take all of our positions and we're going to do xval. And we're going to subset the position, and we're going to take the y vals and subset on, or select the positions that we want. And we got our x and our y, and I'm going to kind of store them into a data frame. All right, and I created a plot with ggplot, and I had a little bit of trouble doing this, but I think I got this. Okay, and so this should correspond to the same kind of probabilities that we see in this table. Okay, so this probability matrix should look like this, except here I've got x on the horizontal axis and y on the vertical axis, and so it ends up being a rotation where you take this matrix and you kind of rotate it. Okay, so across the bottom we'll see 0.02, 0.03, 0.04, and 0.01. And then the second row from the bottom, we will see 0.06, 0.04, 0.2, and 0.1. And so the darkest value is going to be this third from the left and second from the bottom. Okay, second row and third column is going to be 0.2. Second row, fourth column, because again, we're kind of rotating this, is going to be 0.1. And that's what we see. Second row, third column, second from the bottom, third column from the left is 0.2. Here's 0.1. And this corresponds to 0.02, 0.03, 0.04, and 0.01, and so on. Okay, and so these are, so it worked. Okay, so that's how we can generate values from a bivariate discrete distribution. Okay, now we're going to look at the Box-Muller transform, and I've taken these notes. I'm borrowing these from Professor Tsang, and I incorporated Professor Tsang notes into my lecture slides here. But then for the we're going to look at the bivariate normal distribution, and these I'm just going to take directly from Professor Tsang. These are his notes, but they're very good notes, so we're going to just use them directly. Okay, so the Box-Muller transform is a method that we can use to transform two uniform random variables into a pair of independent standard normal random variables. Okay, and so this is a way for us to generate normal random variables, even if we're starting just from uniform random variables. Okay, and the idea here is we're going to switch from Cartesian coordinates to polar coordinates. So if you, we're going to go from x, y to r and theta. And so first we're going to take a look at the joint distribution of two independent standard normal variables. Okay, so x is going to be standard normal variable, random normal variable. Y is a standard normal variable. And their joint distribution, if x and y are independent, is just going to be the product of f of x and the product of f of y. Okay, so the joint density is the product of f and the product f of x and f of y. And so the PDF of a standard normal is e to the negative x squared over 2 times 1 over root 2 pi. And the standard normal over here is 1 over 2 pi e to the negative y squared over 2. Okay. All right, so we do this, and then when you multiply these together, you can combine the exponents. So you get 1 over 2 pi e to the negative, and then you do x squared plus y squared over 2. All right, so this is the joint distribution of two independent random normal variables. All right, and then what we want to do is we're going to switch these to polar coordinates. Okay, so polar coordinates are, we're going to have this relationship, right? X is r cosine theta, and y is r sine theta. So I don't know, maybe it's been a while since you've had to deal with polar coordinates. And then to kind of change from x to y, okay, you take your function, your joint distribution, or your joint function of x, y, and then kind of dx dy, and it has to equal to the joint function of r and theta, dr d theta, right? So as these things change with respect to x and y, they're also going to change with respect to r and theta. So that's what we need. Okay, give me a second. I need to close my window. All right, and so maybe it's been a while since your multivariate class, but this is how you would do your change of variables. Okay, so you have to so kind of looking at this, we're gonna kind of, well, what is the function of r and theta? We're gonna divide both sides by dr d theta. Okay, and so I've got f of xy dx dy over dr d theta, right? And so this, you know, what's this? Dx dy over dr d theta. Well, that becomes the Jacobian, you know, dxy and dr theta, and so the Jacobian. You know, if you forgot all of this, don't worry. It's but anyway, here it is, and so you have basically the determinant of dx dr, dx d theta, dy dr, and dy d theta, right? So you kind of take all the variables as they kind of relate to, as they change with respect to one another, right? So what is dx dr? How does x change with respect to r? Well, if you look back here, when you say, okay, x, and you say, okay, well, what's the partial with respect to r? Okay, well, that's just going to treat cosine theta as a constant, and so we got cosine theta. What's the partial of x with respect to theta? Okay, so we'll say, all right, so we're going to treat theta with partial of theta, and so cosine theta becomes negative sine theta, and r, so we get negative r sine theta. And similarly, you do the same thing for here. How does y change with respect to r? You get sine theta. How does y change with respect to theta? You're going to get negative, I'm sorry, not negative, just regular r cosine theta, okay? So you get this and this, right? And then now you take the determinant of this, so you do this times this minus this times this. So cosine times r cosine theta becomes r cosine squared theta. And then negative r sine theta times sine theta becomes negative r sine squared theta, but then you're subtracting that off, so it becomes plus r sine squared theta. And cosine squared and sine squared is 1. So this becomes r times 1, or r. All right. Okay, and then, okay, so now what we had here, right? So we said, okay, f of r theta is going to be f of xy times this thing, and this thing, we went through all of this. This dx dy dr d theta becomes r. Okay, so this is what we have. Okay, f of r theta becomes f of xy times r. Okay, because this used to be dx dy over dr d theta, and we went through the work and we said dx dy dr d theta is equal to r. And then, okay, so what was the PDF, the joint distribution of x and y? That was back here, 1 over 2 pi e to the negative x squared plus y squared over 2. Okay. And when you switch from Cartesian to polar, the relationship is that x squared plus y squared equals r squared. Okay. So we can replace that numerator, x squared plus y squared in the exponent, the numerator and the exponent, with r squared. Okay. So now my function is 1 over 2 pi e to the negative r squared over 2 times r. Okay. I'm going to keep doing some more work here. All right. And okay, so I can take this function of which is 1 over 2 pi e to the negative r squared over 2 times r, and then what we're going to do another change of variables. Okay, and we're going to look at, okay, well, we got r dr d theta, and we're going to change our variables from r to r squared. Okay, so it's kind of like we're going to replace r with r squared. And so, well, what is dr squared? Dr squared is 2r dr. And so we see this quantity right here, r dr. This quantity r dr is equivalent to 1/2 dr squared, right? Because dr squared is 2r dr. So we have only 1 r dr, which is going to be half of dr squared. So I'm gonna do substitute r dr with this 1/2 dr squared. So that's what we get. Okay, so we have our original function is a function of r and theta, but now we're going to create a function of r squared and theta. And so we got dr squared d theta. I replaced the r dr with 1/2 dr squared. Okay, and so I've got my PDF 1 over 2 pi e to the negative r squared over 2 times 1/2 dr squared. And if I rearrange some terms, I can get 1/2 e to the negative r squared over 2 dr squared and 1 over 2 pi d theta. All right. And if we look at this, this is now going to be the product of two PDFs. Okay. I've got 1 over 2 pi d theta. This is a PDF of a uniform distribution on the span 0 to 2 pi. Okay. So we can say theta is, this is the PDF of theta if theta is a uniform random variable on the interval 0 to 2 pi. And then if you just treat this instead of looking at, if we got r squared here, and if you just call this like x or v or whatever, okay, so if you got this, you got 1/2 e to the negative, basically you can, if you treat r squared as v over 2 dv, that's basically an exponential, that's the PDF of an exponential distribution, okay? So r squared is an exponential random variable where the rate parameter is 1/2. Okay, and this is the product of two PDFs, so therefore r squared and theta are independent. R squared and theta are independent. Theta has the PDF of a uniform distribution from 0 to 2 pi, and r squared has r squared, the variable r squared is exponentially distributed with a rate parameter lambda equal to 1/2. Is that all right? Okay, so with that, we can generate random uniform value. Random normal values. So we're going to start off by generating theta from a uniform distribution on 0 to 2 pi. And then we would generate v from an exponential distribution with lambda equal to 1/2. Oh, quiz answers. Thank you. Thank you for that reminder. Have I given you any quiz answers yet? 0. Okay. All right. I'll give you 2 of them right now then. Okay. The first 2 are C and B. Cat and bear. C and B. Cat and bear for the first 2 quiz answers. C and B. And then I'll give you your last one. Thank you for that reminder. Okay. So we've got R is equal to, we're going to take V from the exponential distribution, and V is equal to R squared. So we're going to say R is equal to the square root of V. We only keep the positive side because the radius has to be positive. Okay, and then we've got X is going to be R cosine theta, and Y is R sine theta, all right? And then X and Y will come from a normal distribution. Okay, and so if we need to generate values from an exponential distribution, we can do that using the uniform distribution. And so uniform 0, 1, if you use inverse CDF method, you can generate exponential values by basically taking the log of it, right? Negative of the log of a random uniform. Okay, so if you do that, then this will become exponential distribution here. All right, and so here's the Box-Muller algorithm altogether. Generate u from a random uniform, and then you make it theta by doing 2 pi times u. So that will go from 0 to 2 pi. Generate v from a uniform 0, 1. You make it exponential by making it 2 log of v, negative 2 log v, and then you take the square root of that to get your r. And then your x and y are going to be r cosine theta and r sine theta. And so this will go map from u and v on the uniform variables, uniform distribution to normal distribution. And so if I run some code to do that, I've got n is 1,000. I generate 1,000 u's from uniform 0, 1, and we're going to make our thetas by doing 2 times pi times u. And then here I've got v is going to be 1,000 uniform values from uniform 0, 1. And then we turn those into exponentials and take the square root to get our r. So I got square root of negative 2 log v. And then x and y are going to be r cosine theta, r sine theta. And if I create a plot, there we go. Random normal variables and a kind of a bivariate, 2 independent random normal variables. Right? There is a very cool picture on Wikipedia. So if you look up Wikipedia, the Box-Muller transform, this picture is really cool. So let me do this. And so it shows here is this area over here is kind of represents u and v going from 0 to 1. Okay, and so what we see is that if I go down this, if I keep v constant, okay, so I'm going to on the horizontal axis is v. So if I keep v constant, that corresponds to the radius. All right, so keeping v constant and changing u changes where my kind of the angle that I'm going around, right? So keeping, sorry, I'm trying to move my mouse in a vertical steady line, but that keeps, it keeps the radius constant, but we're changing our angle here, okay? You know, if I go over here, then when u is, say, close to 0, right? -2 log u takes me, you know, far away. And so v's that are close to 0 correspond to large radius. And so as I move around, keeping the v constant, my radius is held constant, but we're moving around, okay? And then on the other hand, if I keep my u constant, u will gets turned into the theta angle, okay? So if I keep my theta constant, we can see we're kind of moving down one of these spokes here. And if there's a jump, it's only because I can't keep my hand steady. But we're, as I move along here, we're changing the radius. We're changing v, which corresponds to the radius. And so this looks like, so anyway, we get something that looks like two random normal variables, okay? And we basically mapped every kind of coordinate on this span, this 2D space from 0, 1, 0, 1 into kind of all of these random normal values. All right, and so this is a cool visualization, and I think I'll update the slides by including that link there. Okay. All right, okay, and well, we only got a few minutes left, but I want to look at a bivariate normal distribution. Okay, so we looked at generating random normal values that are independent. Now we'll look at kind of random, a bivariate normal where there's some covariance. So this is kind of our goal. We want to get a normal distribution, bivariate normal distribution, but there's now covariance or correlation between x1 and x2, okay? So x1 is normally distributed, x2 is normally distributed, but there's also covariance between them. So you're going to kind of get this ellipse going on. So this is what we want. We want x1 coming from a normal distribution with some mean and some variance. x2 has, you know, mean mu2 and variance sigma 2 squared. And we got a bivariate normal distribution in that the variable, the coordinate x1, x2 comes from a two-dimensional normal distribution where there is this sigma matrix, the variance matrix, which includes a covariance term, right? And your covariance is x1 minus mu1 times x2 minus mu2, the expectation of that value. All right, and so what we want to do is we want to say, well, can we go from standard normal values, okay, centered at 0 with variance 1, can we start there and end up with our bivariate normal distributions where the mean is now mu1, mu2, and the variance is this, right? So when you start off with two independent standard normal variables, there's no covariance term, but can we start off with two standard normal independent variables and apply some kind of transformation and end up with this, okay? So this is what we want to do, okay? We want to start off with two random normal variables, standard normal variables, okay? And we want to multiply this kind of z, this pair of z values from the standard normal. We want to multiply it by a matrix A, and then we're going to add on a vector B, and we want the result. So x is going to be kind of another coordinate of x1, x2. We want that x1, x2 to have the distribution that we want, where the mean is mu x and sigma x, okay? When when you generate two values independently from the normal distribution, the mean is going to be 0, and the covariance is going to be the independent identity matrix with the variance matrix has no covariance here. Okay, has no covariance between x1 and z1 and z2. Okay, but we want to kind of transform this. So we got to find this vector b and this matrix A, so that we end up with these properties here. All right, so what we're going to say is we're going to define x as basically b plus az, and we're going to say, okay, well, we're going to set the expectation of x equal to mu x, and we want this equal to the thing that we want. So, okay, the expectation of x is going to be the expectation of b plus a times z. This is going to be equal to b plus the expectation of az. Z is the kind of the coordinate of two independent standard normal values. And so the expectation of z is going to be the 0 vector. And so the expectation of x just ends up being b, right? So the mean of our x variable is b. And so if we want the mean of our x variable to equal mu, we're going to set b equal to mu. Okay. All right, and we do something similar over here if we say, all right, here's our covariance matrix of x. Okay, x is b plus az. You know, how do we, what do we do to set our covariance matrix equal to the thing that we want? Okay, so x is b plus az. What's the covariance of b plus az? Well, b is just a constant. It's a vector being added, so that doesn't factor into the covariance. So we get the covariance of a times z. Z is our random variable. A is just a matrix multiplied by z. So I can pull a out of the covariance. And so now I've got the covariance z here. And anytime you pull a matrix out of a covariance, just like when you pull a constant out of the variance, it becomes, you square that constant. Here you get a times covariance a transpose. Okay. And the covariance of our random variable z is the identity matrix, because there's no correlation or no covariance between z1 and z2, and the variances of z1 and z2 themselves are just 1. That's just the identity matrix, and so this becomes a times the identity times a transpose, and that's just a transpose. And so we need, what we want to do is we want to set this equal to sigma, the desired covariance matrix. And so we want to find a matrix A so that A transpose equals the desired sigma matrix. All right, so does this look familiar? A transpose equals a matrix? Okay, so we can do that, and we can find a matrix A, and then we call that the Cholesky decomposition, right? So for any symmetric positive definite matrix sigma, you can find a lower triangular matrix A so that this statement is true. Sigma is equal to A transpose. And when you do that, that's called the Cholesky decomposition. All right. So in R, you can just type in Cholesky or Col or something, and it will perform the Cholesky decomposition. But it's actually not too hard to do it yourself. Okay. Basically, you're trying to find this lower triangular matrix where you've got T11, T21, and T22, and a 0 up here, and you want to find, you need to set A transpose equal to the covariance matrix that you have, right? So our covariance matrix is sigma 1 squared, sigma 1, 2, sigma 1, 2, sigma 2 squared. And so A transpose is equal to this, and so when you take your lower triangular matrix and you transpose it, you get this. And you multiply everything out. And so now I have a 2 by 2 matrix is equal to this 2 by 2 matrix. And we're just going to set the terms equal to each other. We're going to say T11 squared is equal to sigma 1 squared. Okay, so that's easy. T11 is just going to equal to sigma 1. And then we look at this term, T11, T21 is equal to sigma 1, 2. And basically, these two equations are exactly equal T11 and T21. So anyway, I can say, well, T21 is equal to sigma 12 divided by T11, and that becomes this. And then lastly, I've got T21 squared plus T22 squared is equal to sigma 2 squared. All right, so sigma 2 squared is going to equal, or I'm sorry, T22, if you solve for this, is going to equal the square root of sigma 2 squared minus T21 squared. And plugging all of this in, you get this. All right, so these terms can be used to figure out your Cholesky decomposition. And so anyway, yeah, I'm just going to kind of zip through these last few slides. Basically, if you figure out this decomposition, then you can create a matrix A, and then you can start off by generating values from the random normal. Okay, 2 independent random normal variables, join them together, and then you do mu plus A times Z. Okay, and that's going to give you X, and X will come from this bivariate normal distribution. Okay, and so that's the algorithm. Generate 2 random normal values from the standard normal, and then figure out the Cholesky decomposition of your desired variance matrix, covariance matrix, and then you set X equal to your mean vector mu plus A times Z. All right, and so if I do that, here's just some code. We're going to just generate 1,000 random variables. Our mean vector is going to be 1, 2. Our sigma matrix is going to be 1.7.71, and then we generate values from the random normal. We could have used the Box-Muller transform if we wanted to. Okay, we could have, but here I'm just using our norm, or we're using our norm here. Mean 0, standard deviation 1, into a kind of a matrix here. We do use Cholesky to find the Cholesky decomposition of sigma, and then we compute X is equal to mu plus A times Z. All right, and if you do that, you end up getting normal random values that are that have some covariance here. Okay, so this is your bivariate normal distribution, and that was I had to plot that. Okay. All right, so that's we'll end here for today. Let me give you your last quiz answer. Last quiz answer is E as in elephant. E as in elephant for the last quiz answer. E as an elephant. Okay. All right, so we'll end here for today, and that's it. Have a good weekend, you guys. Have a happy Halloween, or I mean, as happy as it can be these days. So and we'll see you guys. We'll see you guys on Monday then. So all right, see ya. Have a good weekend.